Hello friends, welcome to my channel. Good to see you all again. I hope you find the stuff I make here very useful. Last year I haven't done much, but I promise to make up for the lost time this year at least. Okay, today we look at a common control principle called duty cycle control, what it is and where it is used. And I have in this presentation not only discussed what is duty cycle control, how to implement it in a PLC, and also I have provided an example. How does it compare with on-off control? Okay, please watch it to the end, friends. Okay, friends, let us begin by understanding the context. Where does the duty cycle control fit in? You see, in typical PID control with analog outputs, what is done is there's a measuring instrument which measures the flow or temperature or pressure or something like that, and then this is taken as an input to a PID loop which compares it with the set point of the measured variable, and then it regulates the measured variable using some kind of manipulated actuator like a control valve or a variable frequency drive or something like that. Now there are two examples given. One is a flow control, simple flow control, where a flow meter is measuring the flow and a control valve is regulating it. That is in the upper diagram. In the lower diagram you see industrial process vessel being heated with steam. Here again, in a similar way, the temperature is measured, it is taken to a PID loop, and the control of the steam is done with a control valve in order to achieve the set temperature. Alright, this is the analog type of control. We'll in the next slide compare this with how duty cycle fits. Okay, now we take a look at duty cycle control itself with a PID loop. In the upper diagram, you see a tank in which the level is measured using a level transmitter. And this is being filled with water through an on-off valve. Now this is not a control valve. This valve will either be fully open or fully closed. Alright. And we are controlling the level by controlling the duration by which for which the valve remains open or closed. It is possible to control the level here like this. In the lower diagram, you will see temperature control being done with duty cycle control. There is the steam valve, but there is no control valve. It is a on-off valve. Now, how does this do? See, between the level controller and the controller and the on-off valve itself, there is a duty cycle controller that determines what will be the duration for which the valve remains open. Suppose if the level is way below the set point, then you can fully open the valve for a very long time. And as the level approaches the set point, you can start interrupting the flow and feed in little by little till we get the set point. Alright, in the second example, we control the same way. There is no control valve which continuously supplies heat, but steam flow is interrupted. Okay. The only difference here is that you need a functionality called a duty cycle controller, which determines the duty cycle or the how long the valve should remain open or closed. Okay, here we go. Now central to the concept of duty cycle control are two things. One is the cycle time, the larger time period within which we are trying to achieve a on duration to all off duration or a pulse width ratio. All right. And the second thing is the duty itself. Means what percentage of the cycle time does the switched output remain on. Okay. There are four examples we see on the right side. The uppermost diagram shows 0% duty, or it is the fully off state. Means during the cycle time as marked by the vertical lines, the output is never switched on. It is fully off, 100% off. Okay, or 0% duty. Now below it lies the 25% duty, where you see it is you get a narrow pulse that is on for 25% of the time. Next, when we increase the duty cycle to duty to 50%, it means it is on for half the cycle time and off for the remaining half. And then for when at 75% of the time, when it is on, you say it is 75% duty. And at 100% duty, it is fully on all the time. It is never off during the cycle time itself. All right. Now next we see why do we need this duty cycle control? What are its advantages and what it can do and what it cannot do? So, why is this important in industry? See, number one is, you get a much better control than with simple on-off control. And for example, in heating process and other things, unnecessary application of heat is avoided. That has got its own advantages, like saving of energy and things like that. You get much better, accuracy of the controlled, process parameter. The second important thing is that these simple devices like on-off valves, solenoid valves and other things, they are much more economical than control valve. And the third thing is, because they are simpler things with less moving parts and all, they can last much longer. You have a more reliable system that lasts longer. But please bear in mind that certain things duty cycle control cannot achieve, such as flow control. It definitely cannot achieve. If you try flow control with a duty cycle controller, you will have pulsating or interrupted flow, which is not a good thing. So just keep in mind, it has its uses. It's very useful. It's very economical. But there are certain things like flow control it cannot do. Okay. Now we discuss the matter of how to implement this kind of duty controller. Okay, many PLCs, I will say nearly all the PLCs have got a built-in pulse width controller. You can use that, apply these same principles what we are discussing here, or you can make your own. All that it needs is that you create a function block with 3 inputs. The 3 inputs are, one is the cycle time. What is the cycle time we are talking about? This variable is got units of time, is a data type time. And the second variable is the duty itself. That is, what percentage of the cycle time do you want the output to be kept on? Okay. And above all, there's a third input called the permit. Now, if this permit is enabled, then the switching can really happen at the output side. That is the command side, where you drive a valve or contactor with that, So inside it, this function block is actually very simple. There are just 2 timers. Both are on delay timers. They are set, they're very simple run. The first timer, it enables the second timer, and when the second timer period elapses, it resets the whole cycle. So you've got two cycles. And rung below it says that you remain on for the duration of the first timer. Okay, so please take a time to look at the procedure. You can very easily make it, and then you have to test it. We'll discuss how to do it in the next slides. Okay, this can be done in any PLC. Alright. Now, you see, when you are declaring the function block, you have to declare what are the inputs and outputs. These are the parameters of the interface. So the first interface you can see is the cycle time. That this is the sum total of the on time plus off time. Okay, then the second is a time variable, data type. Okay, then the second is permit, which is boolean, which is yes or no, true or false. And the third one is duty. We have taken this as a real variable. Okay, so you can get some decimal point control. Now you see the logic itself, written in ladder. The upper rung deals with the business of converting time to real and things like that, And what it does is, the preset period of the two timers and the ratio of the duty cycle is assigned by subtracting the on duration from the cycle time as the off time. Now this off time is nothing but the cycle time minus the on time, right? And the upper rung, you look at it closely. Pause the video and just look at it closely. It is basically just that we are converting the data types, nothing beyond that. It's such a simple logic. Please try it. You will, it will easily work on any PLC. There's nothing. Okay, let us test it out. In the last slide we made the function block, and now I have deployed here as an instance and given it the input variables, demo cycle time of 10 seconds and the duty as demo duty, a real variable with the initial value of 85%. Now if I were to switch it on, you should see the pulses coming out at 85% of the cycle time, and you can see that I switched it on and the output has come out. Let us take a look at the graph and see there are these pulses that seem to be 85%, right? Restarting the histogram, you should see pulses still 85%. They are. Next we'll see what happens when we reduce the cycle time to 25%. This is at 25% duty, we're getting pulses that are 25% wide. Good, that works. Next we will increase the duty to 50% and see what happens. Yes, the on period and off periods are identical. Let's see 90%. See, 90% on time, 10% off time. Now we will reduce it to 10%, see what happens. You should get a very narrow on period. can see that 10%. Finally, we'll see if it completely switches off at 0% duty. And so it does. 0% duty, you get only the time marker, the output is never on. So we can trust that function block and then attach it to a PID block and see how it behaves in, how accurate it is able to control. But before that, we'll see what we get if we do not use a duty cycle control. See what happens with temperature set points and simple on-off control. Alright. To demonstrate this on-off controller behavior, I had made another function block. I'm not getting into this function block for purpose of this video. We'll dig into it in a future video. You can see this green line, what you see is the set point, and the white line is the actual temperature. Okay. So there was a little hysteresis which was given to it, and when you see that the heater is switching on, the body rapidly heats up, and when it is switched off, that is at this point, you can see that the temperature gradually reduces. It swings above and below the green line. That is what you get in on-off control. Now see, this is after all a simulation and there are limitations. In real time, this kind of temperature control is very difficult, and the crossing of the set point on both sides is much larger than it is, to the order of several degrees. You will never get good control on that. It will, to get any kind of stability, you will find that the actual temperature swings in a wide margin, above and below the set point. Most people keep the on-off control with no hysteresis on the upper side. That means most of the time it will be lower than the set point. Okay. Now we test its performance when you connect this duty cycle controller block to a PID block. See, in the background there's the temperature simulator. That is the same thing. The only thing, the controlling method has changed. Okay, now we see the temperature controller is actually working very well. It is more or less following the set point, and you can see that the pulse width is automatically controlled. When you increase the set point, you see suddenly it will remain fully on, and then once again it will start regulating itself. This being a simulation is not very perfect, but still it works well. In the field, because the time intervals are much larger, there you can see temperature set point is increased to 75 degrees, and then the pulse width maxes out to 100%, and then when you hit the temperature, it starts once again holding that temperature. Now all this is simulation and it doesn't look to be working perfectly. But let me assure you that this thing, in larger time constants and a properly tuned PID loop, this will work very well, because there is all the time available to adjust itself. When heating and all, you get several minutes cycle time is par for the course. Okay, to summarize, we have seen that just like in a PID loop with analog actuators like control valve, you can use a digital a thing like a contactor or a control valve heater, with pure on-off control subject to duty cycle control. You can achieve very good results. It is just the same as in any other PID loop. It is also a closed loop control. There are the same sensors which continuously monitor the process variable. There is a set point, and the only difference is that the adjustment side of things, the PLC adjusts the duty cycle of the output to minimize the error. That's it. That's the function of the pulse width controller. Okay. So where is the duty cycle actually used? See, in the electronics world, this is more known as pulse width control, pulse width modulation and things like that. The AC frequency, 50 Hz or any other frequency, can be modulated by a stream of digital pulses, and that is how motor speed is controlled. But let us be clear, this is not a PLC function. That is done by the drive, like a VFD, that can synthesize any frequency up to 400 Hz using millisecond switching times. That is done in the VFD, not PLC. Alright. But as far as process control is concerned, we can find a use for duty cycle control mostly in temperature control and to some extent in level control. Okay, because the time constants in both temperature control as well as level control, it is much larger than in flow control. Okay, this duty cycle control, as I said earlier, is not very suitable for flow control. It will not work well with flow control because the flow will be pulsed, and that has got all kinds of undesirable effects like water hammer and all, and interrupted pulsating flow is not a deciding. Equipment is simply not designed to handle pulsating flows, especially at high pressure. So nobody will control flow using duty cycle, but most commonly we use for temperature control and to some extent in level control. Okay. Towards the end of this session, we come to the kind of actuators that you may use along with duty cycle control. Now, this is very important. Not everything can be frequently, switched on and off, opened and closed, and things like that. For example, a contactor, you cannot open and close it 100 times in 1 second. The thing will simply destroy itself. You have to take care. What is the minimum, switching time allowed? What is the life cycle? How many on-off cycles it is allowed? A small relay will have a life of about, 1 million, 2 million cycles. It is perfectly okay to have a minimum, 1% duty at 1 second, and then the cycle time itself being about 100 seconds. The smaller the relay, you can have lesser cycle time, but bigger relays, you have to see that you have to keep the cycle time large enough to be in hundreds of milliseconds. Maybe then it will work. All right. On-off valve, smaller on-off valves, small solenoid valves, pilot operated diaphragm valves. These have to be operated, within a minimum. They require a minimum interval of about 1 second. So you can have a cycle time of 500 seconds cycle time, 5 second, minimum operating time. That is allowed. Okay. The smaller the valve, less can be the cycle time. Just see the data sheet. What is the mechanical life? How many cycles can be open and closed? What is the minimum operating time and all? The minimum operating time can be taken as a thumb rule to represent 1% of the cycle time. Okay, accordingly. Now with solid state relays, you don't have that problem because there are no moving parts. It is eminently suited. With DC, you can have millisecond switching. Can have cycle time of 10 millisecond and then 0.1 millisecond minimum switch on time. These things can handle it with your DC. But AC, typically the solid state relays are zero crossing. So that means you'll have to factor in that minimum 20 millisecond, minimum on time equal to 20 milliseconds, because that is the uh, cycle time for a single AC cycle. Half AC cycle, you can take it to be 10 milliseconds. Let's say, and these things work very well with heaters. So most often what you will see in industrial control is that certain in machine automation, especially in molding presses and all, heaters are controlled with pulse width modulation or duty cycle control using solid state relays. You can use solid state relays with DC motors to control speed control, but yes, there are certain precautions. You have to have freewheeling diodes and things like that, so that the device is not destroyed with high back EMFs whenever it is switched off. Contactors, as I say, they are not really suitable unless you have cycle times in minutes, at least 2 minutes, and the minimum on time in few seconds. Okay, but industrially, electrical heating or generally heating is what you will normally find with duty cycle control, and to some extent with level control. Okay, so this is all that I have for you today. I hope you enjoyed. Please spread the word about the control philosopher, and if you have any ideas on which you would like me to make a video on, please let me know in the comment section. Thank you, and please see us again.